Apart from differentiating strong acids and bases from weak ones, there are other definitions of acids and bases. Let's look at each of these in turn. An Arrhenius acid is one that ionizes in water to produce H plus ions. To ionize means to form ions. For example, the unionized covalently bonded hydrogen chloride gas ionizes in water to give H plus and Cl minus in aqueous solution. An Arrhenius base is one that dissociates in water to produce OH minus ions. For example, solid sodium hydroxide, which comprises sodium cation and hydroxide anion, dissociates in water. That is, it is split up by water. There are other ways to define acids and bases. The Bronsted-Lowry or simply Bronsted definitions. A Bronsted acid is a proton donor, while a Bronsted base is a proton acceptor. A proton here means a hydrogen atom that has lost its electron. It is also known as a hydrogen ion, H+. Originally, a neutral hydrogen atom has one proton and one electron, but when it loses its electron, it becomes a proton. Thus, H+ is called a proton. In this example, ammonia is a Bronsted base as it accepts or gains a proton, that is, H plus from water to become ammonium cation NH4 plus. Water is a Bronsted acid as it donates or gives away its proton to become hydroxide ion OH minus. Bronsted acids donate protons to water to form the hydronium ion H3O+. The hydrogen ion H+, proton, and hydronium ion H3O+, all refer to the same aqueous species, that is, something dissolved in water. The example here shows the Bronsted acid HF donating its H+ to water to become fluoride ion. Water here is the Bronsted base as it accepts or receives the H+ from HF to become the hydronium ion H3O+. The tiny positively charged H+ ion doesn't actually exist by itself in water. Its positive charge attracts one of water molecule's electron-rich lone pairs. The attraction is strong enough to allow a covalent bond to form between water and H+ to become the hydronium cation H3O+. For simplicity's sake, though, the hydronium ion is sometimes represented as H plus Aq or a proton. When a Bronsted acid donates a proton, what remains of the acid is known as a conjugate base. When a Bronsted base accepts a proton, the newly formed protonated species is known as a conjugate acid. Protonated means to have gained a proton. Conjugate means joined together. For example, after the Bronsted acid HCl donates its H plus to water, it becomes the conjugate base chloride ion Cl minus. The Bronsted base water accepts H plus from HCl to become the conjugate acid hydronium ion H3O plus. HCl and Cl minus are a conjugate acid-base pair, or a conjugate pair. Water and hydronium are a conjugate base-acid pair, or a conjugate pair. A conjugate pair differs by H+. Now, why is a conjugate acid considered an acid? It is because it can donate H+ to the other product, which is a base. And why is a conjugate base considered a base? It is because it can accept H+ from the other product, which is an acid. But as to how well each can donate or accept H+ is another matter which we will deal with later. Note that the conjugate acid-base pair relationship is across the double arrow. They are never on the same side of the double arrow. Speaking of double arrows, we know they are used for reversible reactions. Some say that all reactions can be thought of as being reversible, while others insist that there are reversible and irreversible reactions. Well, we can think of an irreversible reaction as being a reversible reaction in which the equilibrium position lies to the far right and product formation is highly favored. The backward reaction, in which reactants are reformed, occurs to such a small extent that it is treated as negligible. In this particular case, for the reaction between HCl and H2O to form hydronium and chloride ions, although the double arrow symbol is used, the equilibrium position lies largely to the right, as HCl is a strong acid. So it is more accurate to use this other double arrow to symbolize this idea. Now for another example. When the Bronsted phase ammonia NH3 accepts H plus from water, it becomes the conjugate acid NH4 plus. Water this time around serves as a Bronsted acid, so it donates H plus to ammonia to become the conjugate base hydroxide OH minus. NH3 and NH4 plus are a conjugate base acid pair, while water and hydroxide are a conjugate acid base pair. Clearly, in a Bronsted acid-base reaction, an acid and a base must be present. Whether a substance behaves as an acid or a base depends on what it is combined with. Water, for example, behaves as a base when combined with HCl, as shown in the previous example, but in this example, it behaves as an acid when combined with NH3. Water is therefore amphoteric, as it can serve as an acid or a base depending on what it is reacting with. Here are some examples. What is the conjugate base of HNO3, the conjugate acid of O2-, the conjugate base of HSO4-, and the conjugate acid of HCO3-? To find the conjugate base of a species, remove a proton from the formula. To find the conjugate acid of a species, add a proton to the formula. The word proton in this context refers to H+. Hence, apart from removing or adding H in the formula, take care to change the charge of the formula. Part A. Recall the definition of a conjugate base. It is the leftover species of an acid after the acid gives away H+. Identify the acid. It is HNO3. What do we get when we take away H+ from HNO3? We first work with atoms. HNO3 minus H gives NO3. Next, we work with the charge. Recall H+ is a bare proton without any electron. Before it became H+, H had one electron which it shared with oxygen in nitric acid. But when it left without its electron and let NO3 have the electron. Since NO3 now has one extra electron, it is negatively charged. Thus, we get NO3-. Part B. Recall the definition of a conjugate acid. It is the species obtained after a base grabs hold of H+. Identify the base. It is oxide ion O2-. To get its conjugate acid, we add H+ to O2-. Work with atoms first. H plus O gives OH. Next, work with charge. 1 plus minus 2 is minus 1. Thus, we get OH-. Part C. A conjugate base is the leftover species of an acid after the acid gives away H+. If we are asked for the conjugate base of hydrogen sulfate ion HSO4-, HSO4- must be the acid. Remove H first. HSO4- minus H gives SO4-. Next, take charge into account. Like part A, H left without the electron it used to share with oxygen in hydrogen sulfate ion. Thus, SO4- ought to have another negative charge, so it has a double negative charge in sulfate ion SO4-2-. Part D. A conjugate acid is the species obtained after a base grabs hold of H+. Identify the base. It is hydrogen carbonate, HCO3-. add H to HCO3 minus first. We get H2CO3 minus. Next, take charge into account. 1 plus minus 1 is 0. Thus, we get H2CO3. A species does not need to be what we think of as an acid in order for it to have a conjugate base. For example, although we think of the hydroxide ion OH- as a base and not as an acid, it is possible to think of it as an acid. After all, it does have a conjugate base, the oxide ion O2-. In addition, a species that can either lose or gain a proton, such as HCO3-, has both a conjugate base, CO3 2-, and a conjugate acid, H2CO3. Thus, hydrogen carbonate, like water, is amphoteric. Here are other examples. Label each of the species in the following equations as an acid, base, conjugate base, or conjugate acid. In each equation, the reactant that loses a proton is the acid, and the reactant that gains the proton is the base. Each product is the conjugate of one of the reactants. Two species that differ only by a proton constitute a conjugate pair. Part A. HF is the acid since it loses a proton to become the conjugate base F-. NH3 is the base since it gains a proton to become the conjugate acid NH4+. Part B. CH3COO- is the base since it gains a proton to become its conjugate acid CH3COOH. H2O is the acid since it loses a proton to become its conjugate base OH-.